Hello, ladies and gentlemen. Okay, so today we're now going to move past what we've been talking about the relationship between electric fields, electric potentials, forces, etc., capacitance, and talk about some of the other implications that we get from the idea of charges moving around due to forces, right? And this is the idea of something that is very familiar to all of us in our everyday language, something like current, something like electricity, okay? And so this is going to come in a sequence of videos, but this one in particular is really us laying out the nuts and bolts, kind of the definitions, the symbols that we'll be using, and really me talking you through an analogy that I think is very helpful for understanding how all of this goes conceptually. And hopefully that will give us a stepping stone as to when we're ready to start solving problems, which again will come probably by as early as the next video, but no problem solving here. Again, this is just really us talking through what we would typically do in a lecture class about all the backbone, the background information that we need for this sort of thing. So let's jump right in. Okay, so for those of us following along in the textbook, right, for what we use, this is chapter 23, and they just call it outright circuits. And really what we're talking about, like I said, is going to be the basic elements that would go into creating the most simple circuits, okay? The one of which we've used this word before, right, when we first introduced the idea of a potential difference or a potential, we recognized the name of voltage, and voltage represents for us, yeah, it's going to be a battery, right? It's something that gives the potential for charges to flow, electricity, charges flowing, okay? So batteries are going to be the source of our voltage, right? What do they represent? They represent a potential difference. Symbolically, because remember we said we're going to be talking about building simple circuits, and that means we're going to have to introduce the concept of circuit diagrams. Symbolically, they're going to have this symbol over here, okay? Which is a little wire connected at top and bottom, and then these two lines, one longer and one shorter, top line representing the positive terminal of the battery, smaller line representing the negative terminal of the battery, which obviously if you flip it around the other direction would look something like this. So when we see that symbol from here on forward, we're going to think that's a battery, that's a potential difference. Now, because physics likes to confuse you, and we'll see why this is the case, not for a couple of chapters, unfortunately, but there's another symbol historically that people use for voltage, which is not the V with the hats that we've been typically talking about with potential or potential difference, right? It's this scripty looking Greek letter E over here, okay, which stands for the electromotive force. That name kind of tells it all if you think about it, right? It's the thing which is responsible. It gives the motivation for these electrons to move, the electromotive force. It's a misleading name because it's not really a force, right? It's a potential, but remember, the catch is that potential leads to a field, and field can result in force. So there is some reason historically as to why we call it this. So from here forward, when we think of the word potential, when we see voltage, when we see capital V, that's the same as us having this script E. Typically, to differentiate between the stuff that we've been doing where we talk about voltage as a potential difference and as it relates to fields and forces, we would typically call those ones the capital V. But typically when you see it in a circuit diagram, right, you would see the voltage or the potential difference or the electromotive force, all the same word here, right? We would see that represented by this script E. So from here on in, those two things we have to just think of as totally equivalent, okay? Now, that leads us to the idea that what are these things going to do, right? If we put a battery and attach a wire to it, right, we now have a potential difference across the two terminals. We know then that's going to result in an electric field, and then if we placed a charge in it, the electric field would move, right? If charges move, we need a name for that, right? All the charges that we've done up to this point, right? If they did move, we talked about what the charge was doing at point A and what the charge was doing at point B, but we never talked about all the things that resulted in between it getting from A to B, right? That's where the real concept of electricity comes from, when you actually have the charges moving, okay? So we're now in a position to give a formal definition to that, and that's what we call a current. A current, by definition, is nothing more than a measure of how a charge moves, right? Or how a charge changes over some period of time. Great. If the definition is it's a measure of how charge changes in a period of time, like any other definition in physics, then we know then that's just going to be defined as the delta Q, charge change, divided by delta T, time change. So current, we give the symbol capital I. C would be really bad at this point, right? Because we have coulombs and all this other stuff floating around. We don't want to use that, right? We use capital I as current. It's delta Q over delta T, and that's this formula that I'm putting a box around right now. It's units, obviously, if it's a change in charge over a change in time. Charge has units of coulombs, time still has units of seconds, so it's a coulomb per second, okay? And that is such a standard unit. It's one that we like to give a name to because it's so common. We call that 1 amp or 1 ampere, okay? So 1A would be 1 coulomb per second, and that measures current. So if we have a potential difference and we place a wire around it, we can feel pretty much assured that there is some current going through that wire. Okay, how do we represent symbolically a wire in these circuit diagrams? Those are just going to be all of our straight lines, right? The lines that connect the other circuit elements like batteries, capacitors, and the other ones that we're going to introduce. Wires are the things that that connect them together. What is a wire? It's some metal. Why is it a metal? Because metals have no problems having their electrons moved around, right? They can give electrons very easily, right? So when we think of wire, we're never going to talk about the difference, at least in this class, right? That'd be a more advanced circuits class or a standalone circuits class. We're never going to differentiate between the difference between copper or aluminum or something. You know, it's a wire. A wire is a wire, and what does the wire serve to do? It serves to be a charge carrier. It allows the charge to flow, right? And so when we connect those straight lines, like in this very, very simple circuit right down here, right, where we're just putting a battery or a voltage or an EMF, right, and connecting the two terminals, right, we made a closed loop. We made a circuit. A circuit, by definition, is just some sort of closed loop of wire with some elements, okay? Now, the big introduction here is going to be the concept of what's called a resistor, okay? And resistor is going to take on a lot of different things, like, for example, like a light bulb is considered a resistor, okay? What is a resistor? A resistor is going to be something in our circuit which will restrict the flow of current. Namely, it's going to be something that causes you to pay a price. Like the charge, if you're in a wire, you got nowhere to go. If there's a resistor in your way, you got to flow through it, right? So charge got nowhere to go, and we know charge, one of our basic conservation laws, can't be created nor destroyed, right? So charge has got to go through this thing, so something's got to give. What's the thing that gives when you go through a resistor is it's going to be something which not just restricts the flow of that current, it's going to be something that changes your overall potential, right? You putting a resistor, light bulb, onto a battery, right, reduces the potential difference in the battery, right? After a while, the battery dies, okay? That's what's going on here. You pay some price. And so the resistor is going to be the price that we pay while we're making our journey around the circuit, okay? Resistors typically have this symbol, this squiggly line symbol, okay? And we say that those objects have some sort of resistance. Just like how when we introduced the idea of capacitors, right? We said that an object can have a capacitance, and anything that has a capacitance can be called a capacitor, right? Here, any object with a resistance, like a light bulb, can be called a resistor, okay? Its units are in ohms, this Greek letter omega down here, and we'll talk more about that in a little bit. Capacitors we're already familiar with, right? They come with a ratio, or they come as the definition of the ratio of an object's charge to the potential difference, and their symbol looks like the thing that we've been talking about mostly with capacitors, which is a parallel plate. They look like a mini parallel plate, which obviously then is going to look like this one if it's standing up on its head, or this one if it's drawn to the side, okay? So again, to summarize, right, when we have a circuit, we're going to be drawing the following symbols to represent these concepts that we know about, right, namely a potential difference, right, which looks like that, a resistor, which looks like that with some resistance R, and a capacitor, which looks like that. And wires, obviously, then, are the things that can possibly connect them. Now, although you might think, well, geez, that sounds really boring, right? What possible circuits can we make with just batteries, resistors, and capacitors? As it turns out, you can make everything with them. Okay, it sounds, we call this simple circuits, but outside of transistors and a couple of other things like diodes, which are, again, not for this class, you would be utterly amazed how many circuits we can use just by wires, potential differences, or batteries, resistors, and capacitors. Now, the good news for us is that we're only going to ever at one time be focused on a particular type of circuit. Namely, you're always going to have a battery because you're always going to have a potential difference, right? And then connected to that battery, we're only going to ever have one of two possibilities. Well, I guess you can always have more than one battery, right? But outside of that, we're always going to only have circuits that consist of nothing more than batteries and resistors, or batteries and capacitors. We are never in this class going to link capacitors and resistors together, because that would require calculus, and that's outside of the scope of this class. It's a fascinating thing that happens when you have capacitors that can be charged according to the way the current is flowing, and then how they deploy to the resistor. But again, that's not for here. So we're only going to have to worry about doing these with one type of object in the system. And for the moment, we're going to focus on the idea, or at least for the next 2 or 3 videos, we're going to focus only on the idea of batteries, wires, and resistors, okay? So we said, let's list out those are the elements that go into these things, okay? Now let's list out some simple properties that these have to have, okay? And these are properties that if we think about it long enough, okay, they're properties that actually make a lot of sense. And it's all the information that we're going to need literally for the next 2 or 3 topics. So if we can get our head wrapped around these properties and why they're true, then we're going to be in really good shape to get through the next stuff, okay? And we'll see how this all goes, I promise, okay? First and foremost, we said that if you're a circuit, right, you complete a loop, right? So you have to have a closed loop, or else the circuit is broken and then charge won't flow, okay? Why is that? Because the way the battery works, right, is that if you want to set up that electric field, you have to be able to flow from the negative terminal to the positive terminal. And then, so therefore, we have to have wires connecting this to make it happen. So a simple circuit, as we know it, has to have a closed loop, or else it's just not even on the table for us. It's not interesting, okay? We need a battery in there to get something going, to get current, right? To generate a current, we need a potential difference. We need that voltage in there, okay? So we know that a potential difference can be defined between any 2 points, right? So if I look at this circuit in the top right, where I have I just pick any 2 points between A and B, right? I know that's the potential that exists between A and B. But if I drew those 2 points right next to, my apologies, if I drew those 2 points right next to the terminals and nothing else was going through, if we weren't paying any price or we weren't going to any resistor, then the potential difference is still the same there, right? So the potential difference, we can pick any point that we want and define the potential difference between that. And all of it is going to be in some way related to the battery or batteries in the system. Clearly, okay, if we think back to how we first defined potential difference, right? Remember, potential comes from KQ over R. R is the distance, right? If we ask ourselves, what's the potential difference between 2 points, and those 2 points are the same point, right? What's the potential difference between A and A? Well, it's got to be 0, right? The potential difference here has got to be the same as the potential here, yes? Okay, because KQ over R here has got to be the same as KQ over R here if we relate it back to our original thing, right? And so the potential difference from point A to point A has got to be 0, right? You can't have a potential difference if you didn't move anywhere, okay? That's very important, actually. okay? Because yeah, that makes a lot of sense if I only say, well, if I start at A and I don't go anywhere, right, I just stay at A, the potential difference there is going to be 0. I haven't paid any price. But here's the catch, right? That has to be true no matter where we go. Let's think about this, right? If charge was to leave A and migrate around, yes, it might pay a price at a resistor, then it comes down and it keeps going, it goes through B, but then it flows back through the battery again in order to get back to A, right? It gets its paycheck, right? It gets its wallet back when it goes back through the battery. Everything it lost comes back. But again, if where we go, or sorry, if where we started ends up being where we ended, again, the potential difference between those 2 points has still got to be 0, right? This is just like saying, the good old, remember James, the headset and the spandex, right? That if we want to do the physics workout video, how is work defined? It's force times a change in distance. If the change in distance is 0, you've done no work. Remember that work is related to potential energy and is therefore related to potential. So if the distance you went, even if you actually moved somewhere, but if the ending place is the same place that you started, right? The delta, the change in that as a whole is 0. And so the potential difference, not only for staying still, but the potential difference around any closed loop has got to be 0. That is super important, right? That makes a lot of intuitive sense, I think, when you have a circuit that just has one and only one loop. The potential difference around that loop has got to be 0. But what about a circuit with many loops? Well, it's got to be true for any one of those loops within a circuit. The potential difference, again, if you call one point in that loop a point A, and then you do whatever you want, but you still come back to that point, that net potential difference has got to be 0, just because it comes back to our basic definition of work, and we're back to our workout video. We call this something fancy in physics, but we don't even have to worry about that fancy name, right? This is one of what is called Kirchhoff's circuit rules, namely the loop rule, that basically says that the change in potential around any closed loop is 0. We don't have to think about it as Kirchhoff's anything. We just think about it as to what it is, right? Potential difference means that you have to go somewhere, but if the place you go is where you started, you've went nowhere, right? The potential difference is 0. Okay. The other thing, which also gets a fancy Kirchhoff name, right, is something else that should make a lot of sense to us, right? We said that when we draw circuits, right, current's got to flow, right? So if current's flowing, yeah, here it goes, it's flowing. I'm just going to zoom in so we can see this color come out a little bit better, right? Current's flowing. Let's say there was a current of I sub t for I total, right? And that current flows, and all of a sudden it hits a junction. Well, some current might say, well, I kind of like this road because this road's got a pizzeria on it, and I kind of like this road because this road's got it's got Burger King on it, right? And so let's say some of the current goes up in green and goes through the resistor and comes over here. Some current goes to Burger King down here and comes back. The analogy that we're going to say is that Burger King or the pizzeria, these are friendly places, right? You don't go in there and get killed. You're a charge. What's the same way of saying that? Right? Is that all the charge that went into Burger King or the pizzeria, all those charges come out. Okay. So at the end of the day, if you started with I total of current, and some of the current, i.e. charge, went to Burger King and some of it went to the pizzeria, and then you meet back up in the street to go to the next place, how much of it meets back up? We're back to the total current or the total charge again. How do we know that has to be true? It's conservation of charge. Charge cannot be created nor destroyed. So when it flows through something, a capacitor or a resistor, okay, yes, something happens, right? We pay a price. In order to eat at the pizzeria or to eat at Burger King, we got to pay for that food, right? That's the potential difference that we pay. But the amount of charge that goes in, no one dies at Burger King, no one dies at the pizzeria. So the amount of stuff that goes in, it does whatever it's going to do, it pays its money, and then it gets back. And then if it comes back, eventually makes a closed loop, its net change in potential or the net price it would pay would be 0. Okay, so again, that is nothing more than conservation of charge. Again, we give that a Kirchhoff name. We call that the Kirchhoff junction rule. Why? Because we're saying that the current that flows into a junction is the same as the amount of current that flows out of the junction. But again, we don't have to call it that. It's just conservation of charge. All the charge that goes in has definitely got to come out. The big question then that's left over is that, okay, if we go to Burger King or the pizzeria and we pay a price, right? How much price did we pay? And this is the new one. This is the real important one. This is one that's called Ohm's law, okay? And what it says is that the voltage, right? Again, that's our money, right? The potential difference, the voltage, the price that we pay to go to either the pizzeria or the Burger King, right? Is that we pay the amount of current that's in that system, I, times the resistance of that system. It's obviously going to be for capacitors, again, which we said we're going to skip on capacitors for now, right? But it's obviously going to be, well, if C is just Q over V, right? Then we know if we solve that for V, we just do the simple algebra and we get the same type of looking thing. But for here, for our purposes, the price that we pay to go through a resistor, right, is given by this formula here. V is equal to IR, and that's true for any resistor with its respective current going through it, gives you the net potential that you lost for going through, or that you paid, if you will, because sometimes maybe it's a bank and it gives you money. And we'll figure out how we differentiate between Burger King and banks in the next video. But key takeaway is that if we go through a resistor, something happens, right? We change the voltage. And then if we go around an entire cycle, what is the net voltage change? 0. And again, just like how the loop rule that we talked about a minute ago, that delta V was equal to 0 around a closed loop, this Ohm's law is also valid for any part of the circuit, the main loop of the circuit itself. But if that circuit has subloops, this law has to be true for those subloops as well. Okay, and so basically, what's going to happen? If we're forecasting the future here, okay, what we're going to be doing in the next couple of videos is really just exploiting this one formula over and over and over and over and over and over again on circuits that look, you know, different layers of complexity more and more and more. Okay, that is the real crux of the definitions. And so I want to summarize again, because it's very important for us to have the takeaways from this video before we jump into the next video, which will introduce a little bit more definition-wise, and then jump into some actual problem solving with this. But again, the key takeaways is this part, right, was us giving definitions. Electromotive force, script E, is the same as voltage. I, change in charge over change in time, is defined as current. Wires serve the purpose of carrying the current. Resistors is something which changes the potential in order for something to physically happen. Circuits are loops, or else nothing happens. When we have a loop, since we are free to pick points at any points along those loops, if we have two distinct points, the potential between A and B makes a lot of sense. If we have 2 points which are the same, potential at A, and who cares what you do, but you still come back to the potential at A and you ask, what's the potential difference between A and A? It's got to be 0, because that's potential, again, relates to potential energy, which relates to work, and work requires you to have actually moved a distance in order to get a net work, and therefore a net change in potential energy, which therefore a net change in potential. So unwinding that again backwards and trying to reiterate that same point, around a loop, the change in voltage is 0. Doesn't matter if it's the main loop of a circuit or some sub loop in a circuit. Current, if it's flowing down a wire and that wire gives it more than one option as to which way it can go, right? If we're thinking of it like us, we're the electrons just kind of like marching down that wire like, oh yeah, let's go, let's go, let's go, let's go, right? We go, and then we get here and boom, we have a choice to make, right? Which way do we go? Well, some of us go up, some of us go down, but we can't go to both. Can't go to both, right? We got to get home at a certain amount of time, right? So some go up, some go down. But after we do our thing of each going up and going down, we all come back together at this other point over here, right? And we move off together because these are friendly pizzerias and friendly Burger Kings or friendly banks or whatever the case may be. And so when we go into a junction, the total current that went in is the same as the current that comes out. Oh, well, it would help if I actually wrote the right thing here, yes? The amount of current that goes in is actually the same as the current that goes out, no matter how complicated the junction is, okay? And that's very important for us to keep in mind because that's going to, again, come up over and over and over again, okay? And again, where does that come from? It's nothing more than conservation of charge because current is defined as the change in charge over the change in time, okay? So if charge has to be conserved, and these are things that are neither creating charges nor destroying charges, then therefore current, since it's based on just being charge divided by time, also has to be preserved. And so that is the junction rule. Okay, again, we're probably never going to call it that. We're just going to call it conservation of charge. Last but not least, the big takeaway, right, is then what price do we pay or how much does the bank give us when we go to a resistor, right? The net change in potential at a resistor, or the voltage that you pay or the voltage that's given to you, is a measure of not the overall current, not the overall resistance, but of the current that went through that resistor multiplied by the resistance of that resistor. So if we just go right back up here, right? Here was a thing where the current had a choice. Some current went up, some current went down. I1 went up, I2 went down. Let's say that these were two resistors, R1 and R2. Yes? Do we all agree then that the potential difference or the potential that I pay in the top loop is not I total times R, it's I1, R1, V2, I2, R2. Whereas opposed to if there was a resistor out here, R3, and I asked you to apply Ohm's law to that resistor, V3, do we all agree, would be not I1, not I2, but I1 plus I2, also known as I total, times that resistor 3, okay? Again, we're going to be applying this formula systematically over and over and over again to these systems, no matter how complicated that we make them, okay? I want you to digest this before we start introducing a little bit more notation, because really this is the big important piece. If we miss this stuff, none of the rest of the stuff is going to make sense. But if we wrap our heads around this and realize that this is really not so bad, we're going to be in great shape for the next piece. Okay, so in the next video, we're going to talk about, well, when we have these branchings and we combine, you know, because notice that in each one of these branches, there was only one Burger King or one pizzeria, right? But you know, busy streets from wherever you're from, right? Even streets down in Springfield, right? They don't just have a Burger King or a pizzeria. Some of them have a Burger King and a pizzeria. Well, that means the people that went to that road, yeah, they're really hungry. They got to stop at both places, right? Because if it's in the way, you got to keep going, right? So you got to pay that price. So how we have combinations of these things is what we're going to figure out next time, because the world of circuits is much more interesting than just having a wire attached to one resistor and a wire attached to another one, and then we come back together. Sometimes those sub branches can get quite complicated, and so we have to figure out how to resolve those things. Again, that's where we're going, but make sure that this makes sense before you jump into the next video. Once you jump into the next video, we'll talk about those different combinations. We'll even start doing some problem solving there, and then we'll be ready to jump into actually diagnosing some simple circuits. Until then, ladies and gentlemen, I hope that you found, again, watch this one ad nauseum if you need to, because it's the one that you're going to need in order to get the next couple of weeks. And you know, you're going to see that although it sounds like a lot of jargon right now, it's really not so bad, okay? As always, if you have questions, comments, complaints, or concerns, please don't hesitate to send them to me. I look forward to seeing you all within a couple of days, and have a great, great night.